Recall one of our favorite functions in calculus is the exponential function. Remember that the derivative of e to the stuff is e to the stuff, right? Of course, we have to remember the chain rule, but it's its own derivative. And so that gives us a nice integral rule that the integral of e to the u du is e to the u plus a constant, of course. So we're going to just get some practice recognizing, recognizing this form and integrating when we do see it. So if something fits the if something fits the exponential form, u has to be the stuff in the exponent. Not everything is going to fit. Not everything that with an exponential function is going to fit the exponential form. Case in point, the last example in the last section involved e to the stuff, and it wasn't an exponential form. But if something does fit the exponential form, we have to let u equal the stuff in the exponent. So in this case, if we let u equal x squared, du is equal to 2x dx. I'm off by a factor of 2, so I'm going to put that in, compensate outside. Now what we have is e to the u, and this part here is du. E to the u, the integral of e to the u is e to the u, so this is 1/2 e to the u plus a constant, or 1/2 e to the x squared plus a constant. If something fits the exponential form, it is the integral of e to the u. It is not 1 over e to the u or e to the u all squared or anything like that. It's just simply e raised to the u power. So sometimes we might encounter an integral that fits this form after we rewrite it a little bit. So here I've got dx over e to the 5x, and so initially it might seem like, oh, we'll let u equal 5x. However, if I bring this 5x up, because I don't want e to the stuff in the denominator if it fits the exponential form, this is actually e to the negative 5x dx. And now it's easier to see that we should let u equal negative 5x, so that du is negative 5 dx. I'm off by a factor of negative 5, but that doesn't bother me. I'm going to throw in that factor, compensate outside. Now I have negative 1/5 times the integral of e to the u du. This integral with u's we know how to do. The integral of e to the u is e to the u plus a constant. Throwing our expression back in, we get our final result here. One more example. This one is a definite integral. So when we make our substitution, we'll also switch up our limits. It's not immediately clear what our u substitution should be. First of all, we'll just note that we do have exponential functions, but the powers are different, right? So letting u equal e to the x isn't really going to work that well because we don't have another e to the x. Letting u equal e to the 3x plus 1, or letting u equal 3x plus 1 might not be so helpful, because then what do we do with this e to the x in the bottom? However, let's see, I think I'm just going to yank out that factor of 3 first. That makes things a little bit cleaner. One thing we want to remember, if this does fit the exponential form, I'm just going to write out what the exponential form looks like again so we can see it, have it in front of our faces. It's the integral of e to the u du. That's the exponential form. So I want a single e to the stuff. So if I look at what I have and I think about, oh, can I write that as a single expression, e to some stuff? We actually can if we use the rules of exponents. We're dividing. The bases are the same, right? The bases are both e, and we are dividing. So this is e to the 3x plus 1 minus x, if I subtract those exponents. E to the 2x plus 1. Now that we've rewritten it using some algebra, we could see what, I hope we could see what might be a good substitution to make. Go ahead and pause if you want to give it a go before I say what I think a good substitution is. I'm going to let u equal 2x plus 1. That's the stuff. If it fits the exponential form, it's got to be the stuff in the exponent. And then du is 2 dx. So we actually need a factor of 2 here. So I'm going to throw that in, compensate on the outside. And now while I'm at it, because it's definite integral, I'm going to switch up my limits. So x equals 0 means u is 2 times 0 plus 1, or just 1. X equals 0.5 means u is 2 times 0.5 plus 1. That's 1 plus 1, or 2. So we're integrating. Now I'm going to rewrite it with u's. Now it's e to the u du, and my limits are from 1 to 2. Now, the whole point of making the substitution is that this integral should be easier to do. It fits the exponential form. The integral of e to the u is e to the u. It's a definite integral, so I don't need a plus c this time. So 3/2 times e to the u evaluated from 1 to 2. I'm going to plug in my limits. Or 3/2 times e squared minus e. There it is as an exact value. I can also approximate it. .006. Either is fine.